Please welcome Thomas Graf.
Good morning, everybody. So first of all, thanks a lot to Bruce for having me here and having me in your track. FutureNet is all about predictions, and my prediction is very simple. Layer 7 is going to be the new layer 4, and I'm going to explain why. But before I dig into that, so who's this guy talking to you, apparently trying to sell you DPI? So my background is in Linux kernel development. I have been part of the Linux kernel team for the last 15 years, helping to build possibly the biggest monolith ever, right? A monolith built by thousands of people. For the last 2 years, my focus has been on BPF. And Brandon talked a lot about BPF and XDP and how it's revolutionizing the kernel. It's revolutionizing the kernel in multiple aspects, in networking, security, and tracing. We heard a lot about networking. It's also changing security from a sandboxing perspective. It gives us a new tool set to create sandboxes to sandbox applications. And it revolutionizes tracing because all of a sudden we can see and run an intelligent program at the point where an event is happening and create histograms and so on. So it's basically giving us the ability to actually trace and profile production systems at high packet rates or high system call rates and so on. Given that Brandon talked a lot about BPF use cases already, I want to show you one example. One example that I think was the aha moment for a lot of people. And this moment was when Facebook presented their numbers that they saw when they switched from IPVS-based layer 4 load balancing to XDP BPF-based load balancing. So Facebook, first of all, I'm not working for Facebook, so I'm basically repeating what they put out there at NetDev. This is a conference for Linux kernel network development. So they're running ECMP, L4 load balancers, and then an L7 load balancer. And they have been running IPVS. IPVS is a Linux kernel technology that allows you to load balance. They have been replacing that with XDP, and they saw a factors better performance. And this is something that doesn't happen that frequently. So this is a real game changer in terms of how we can do networking at speed in software on Linux. What I want to talk about is something else, though. And I think BPF has much more potential. And to give you an idea what I mean with that, I want to step back and take you through the process and the evolution of how deployment and server infrastructure networking has evolved. So many years back, we had individual servers. They were set up. We would deploy to them every couple of months. Typically, this would be a mail server running on a server. We would literally manually install the server and install the software. The age of virtualization came around, and we would run VMs. Typically, we would deploy 3-tier apps. We would deploy monthly. But it was still pets, right? We're now entering the age of microservices, service-oriented architecture. You can call it whatever you want. What all of these have common is that we use techniques like CI/CD. We have agile development teams. We deploy multiple times a day. What this has brought us and what this required was automation tools. So we have many tools that will automate the deployment, monitoring, the building, deployment. All of that is automated. If you're looking at networking, though, in particular network security, it has not evolved that much. It's barely evolved. It's still based on filtering on ports and IPs. Whether that's IP tables, whether that's flows, OVS, it doesn't matter. All of these are based on IPs and ports. So why is that not good enough? Is it good enough? We're looking into an example, and the example is a very typical pattern that you will see in most microservices application. They typically use protocols like gRPC, REST, and so on. These protocols require you to open up port 80, port 443. At this point, everything will run over that port. So basically, as you open up your firewall to allow that port, you open up the gate for everything. And your entire API service is exposed. So let's look at a very specific example. And this example, in case you don't know Gordon is the mascot of Docker. So Gordon is an intern at the company, and he has a brilliant idea. So the company is struggling with filling their hiring pipeline. So he believes I'm going to write this awesome microservice. It's going to use that API that has all the chop offerings, and it's going to tweet them out, right? So he writes that service. So he writes the service on the left, which is the tweets service. And he's using the API of the chop service. So the chop service has this API, and this API has, first of all, a health function. So this is something in microservice stack where you can basically check the health of your microservice. So it will return, I'm healthy or I'm not healthy. It has an API to retrieve the jobs. It has an API to retrieve the applicants who applied for the job, and you can post new jobs. So this is how a typical REST API could look like. So Gordon needs to use the get jobs API because he wants to retrieve the current job offerings and then tweet them out. So he does that API call, right? As he deploys his application, his microservice, he has to allow for this communication on the network. And typically, this will be a flow like this. It will say, I'm allowing layer 3 from the IP of my tweet service or from all the IPs of my tweets service containers to port 80 TCP, and this packet should be allowed. And this will allow the tweet service to talk to the chop service. But what it also allows is for the tweet service to access all of the other API endpoints. So the tweet service can all of a sudden also check the health. It can retrieve the applicant's data, even though it's not supposed to and it's not required. That's not least privilege security. Like the CISO is definitely not amused. In the age of microservices where we deploy multiple times per day, we're running microservices built on top of open source software. We're running millions and millions of lines of code in our data centers who you've never read. Like none of the engineers have read them. They will import Golang packages, use them, very agile, very fast, but you're running code written by others. What happens if that code is not behaving the way it should? You need to restrict your microservice to least privilege. So what do we want? Going back to this example, we want to be able to restrict to the least privilege, to the minimal API service that is required to fulfill the functionality. So we want something like this. We want to be able to say, if you are consuming the chop service from the total tweet service, you should only be able to do the get/jobs API. That's least privilege on layer 7, and this is why I think layer 7 is the new layer 4. This is the new standard, this is the new minimal standard for network security. You still need to do layer 3 or layer 4, but layer 7 security, API security is the minimal. Adding layer 3 and layer 4 on top is, you should also do that, but it's not the other way around. Layer 7 security is not nice to have, it's a requirement for the microservices age. So what options do we have today to do this? And some of this might look very familiar from way back, because there's this new concept that is evolving around services mesh and sidecar proxies. And some of you have never heard about Sidecar proxy. It's not much different than way back when we had inetd and TCP wrapper, right? You basically run a process that sits in front of your application, accepts the connection, and then passes on the requests. So how does that look like? So we have two microservices talking to each other, and we will inject a sidecar, so-called sidecar proxy, in front and after each service. So any connection, any layer 7 connection that goes into the service and comes out of the service goes through that sidecar proxy. And that sidecar proxy can perform various functionality, security, routing, layer 7 load balancing, rate limiting. It can retry requests if a backend service is becoming non-functional, and so on. So this is becoming the new layer 7 world. So the sidecar proxy is basically a data path. And then on the management control plane side, we have projects like Istio, which was recently announced. I think Franz in the next session will talk more about Istio. So Istio is basically the management control plane that will orchestrate the sidecar proxies and will perform additional services like CA and API management and so on. So basically the control plane to your services mesh. That sounds neat, right? So that solves my problem in terms of being able to enforce security and routing functionality on layer 7. How does that look like on the network? So this is how it how a typical service-to-service connection looks like. Very simple. Service sends data, goes through a TCP stack, sent over the network. The remote node receives it on a TCP stack, passes on to the application. As we introduce a Sidecar proxy, we have to pass through the TCP stack multiple times. The application sends the data. It goes through the TCP IP stack. There will be an IP tables rules which redirects all the traffic back into the Sidecar proxy. So it goes back through the TCP stack. The Sidecar proxy accepts the connection, looks at the request, performs the layer 7 services, and sends out all the data again. It has to go through the TCP stack again. So even just to get the packet out on the network, we already passed through the TCP stack 3 times. And then the same thing, the same procedure will happen on the receiving node. So from going through the TCP stack twice, we're now going through the TCP stack 6 times. That means 3 times the amount of memory resources. So socket memory is something that consumes a lot of resources, which means as you consume public cloud and your services all of a sudden require 3 times the amount of socket memory, that will require you to run bigger VM instances, which is something that will have an effect on your cloud bill. It also means, as I mentioned, the 3 times more TCP stack traversals. And obviously lots of context switches as we require to go through 2 additional user space applications. And it introduces complexity. From 1 network flow, we went to 3 network flows just for 1 direction, right? So can we turn that sidecar into a race car? And this is where BPF is coming in, and this is where the Linux kernel is coming in. Because if this is the new minimal requirement in terms of network security and security for microservices, that should really be a property of the operating system. Why does the Linux kernel not provide this functionality? If this is a core functionality to run applications securely, that should be a property of the operating system. So why hasn't this happened? It's because we didn't have the technology before. And this is where BPF comes in, the superpowers of Linux, right? So Plumgate IOIs basically planted this seed a couple of years ago, and it's now been growing, and it's the fastest growing subsystem in the Linux kernel. It's evolving very, very quickly, and I think it's changing networking, security, tracing, profiling, and I think in particular software-defined networking. So how can I use BPF for my microservices? About 2 years ago, we started the project Cilium. So Cilium is an open source project. It's bringing BPF, XDP to microservices. It's making the Linux kernel microservices aware. How does it look like exactly? So BPF is a kernel technology. How do we configure this kernel technology BPF? Cilium runs as an agent on all your compute nodes and has plugins which connect the orchestration system, Kubernetes, Mesos, Docker, retrieves events when containers are started, when networking is required, and will translate that into BPF functionality. Cilium will look at the intent of your container and generate and compile a BPF program that is specifically tailored to that container only, which means it's basically the next phase, I would say, of SDN. It's not configuring it, but it's actually writing a specific program on the fly for that container. So for example, the IP addresses of the container, the MAC address of the container is hard-coded into the program. This is not configuration. It's part of the program. If a container does not require IPv6, we will simply take out the IPv6. We will not compile in IPv6 code. If it does not need port mapping, we will leave that code out. So we can generate and inject the minimal code size required. So that's the core functionality. It's the core promise of Cilium. Cilium consists of the agent that runs on every worker node and would be orchestrated by something like Kubernetes. It has a CLI to interact with it. It has a policy repository, and it has a Cilium monitor, a monitoring functionality. And this is something that is also changing the way we've been able to do network monitoring. Because through the use of BPF for tracing, a data structure has been written, the perf ring buffer. So it's a fast ring buffer structure, per CPU ring buffer, that allows the kernel to expose events and samples to user space at very high speeds. It's been intended for tracing, for sending millions of samples to user space. We're using this for network monitoring. So we can literally monitor production rate or production level system in terms of packets per second. which previously, if you would run TCP dump, this would have a massive impact on your system performance. So how does Cilium relate to layer 7, and how does that turn my sidecar into a race car? And this is where K-proxy is coming into the picture. So K-proxy means kernel proxy. And it's actually a simple idea. Can we move that sidecar proxy that's running in user space, can we move that into the kernel? Yes, we can. Why was that not possible before? Because the kernel did not have TLS support. But this is changing. The kernel has KTLS, kernel TLS support now, which gives the application the ability to share the SSL certificate with the socket, and gives the kernel the ability to see the clear text that the application is sending, even if it's using SSL. So if K-proxy, the TCP connection, is not redirected into user space, into a proxy, but we're performing the layer 7 services on the socket where the application is sending this. So before any network packet is even crafted, so the application does write system calls, sends the data out into the socket. We look at it, and only if it passes our policy enforcement engine, and after we've performed routing, we would actually go into the networking layer and construct TCP packets. So we went from this complex picture with 6 TCP stack traversals to a very simple and easy to understand architecture with minimal overhead. So how does K-proxy, Cilium, kernel, Envoy, Linkerd, Istio, how does this all fit together? This is how I see the stack going forward. I see a Linux kernel that's in love with BPF, obviously, performing kernel-based sockets, socket filtering, socket terminations, basically a socket proxy. I see BPF-based layer 7 protocol parsing, in particular for protocols that are easy to parse, such as Kafka. I see socket redirect, so the ability to redirect into other applications on socket level. And I see a BPF-based policy networking and load balancing layer. Orchestrated by Cilium that runs as an agent and connects this engine or this data path to your microservices orchestration system. In case the kernel cannot handle a protocol, for example, if the protocol is too complex or the kernel is lacking a particular protocol parser, we can fall back on the existing sidecar proxy model. And we can not only do this on a per connection basis, we can do this on a per request basis. So even for an existing connection that's ongoing, that's sending multiple HTTP requests, if one request is too complex to parse, we can simply give up and say, this is too complex, we need to go to the user space sidecar proxy. It may also be required to actually verify the API call against the external service and figure out to check whether the API call is supposed to be made or not. In this case, you would also go to the user space proxy. And then on top of this, Istio, a project that was announced by Google, IBM, and Lyft a couple of months back that will provide orchestration of these sidecar proxies, provide CA services, and provide proxy management. So in the end, the picture will look relatively simple. This will not be complex. We'll have an application sending data on sockets. No change to the application. Sharing its SSL certificate with the socket. We will have BPF and K-proxy looking at the data, performing layer 3, layer 4, layer 7 services. If needed, we can go to the sidecar proxy and come back and then send it out the network. On the right side, we see the cluster-wide management services, integration with Kubernetes, Mesos, Istio, and possibly also. I've listed Kubernetes, Mesos, so that's the orchestration systems that we support right now. So this is not something that will add lots of complexity. It's the introduction of K-proxy and BPF will simplify the picture and will allow you to run sidecar functionality in race car mode. And with that, before I close, usually I would give a demo because I'm a big believer in demos. Unfortunately, this session is 20 minutes, so we didn't have time. But we do have an awesome Star Wars demo. You should definitely check it out. The demo was given at DockerCon a couple of months back. The link points you to the YouTube video directly. We also have a Getting Started guide where you can try out Cilium in 10 minutes It will run on Minikube, so it's a minimal Kubernetes cluster that you can run on your laptop in a Vagrant environment. You can enforce layer 7 policies in 10 minutes. And there's also a link to the GitHub project, so obviously this is an open source project. With that, I'm closing. Thanks a lot.